Hi, so it's finally time for the light portion of our chapter 11 waves. So what we're going to do now is on the board here are the important some of them, the important equations and values that we need to know. So of course, I recommend writing these down. The first one is the velocity of light, which of course V equals velocity 3.0 times 10 to the 8th meters per second. Okay, so putting that into perspective, light can travel around the world in 0.13 seconds. That's how fast light travels. And that concept is going to become important to us as we do some of the problems along with math and the speed, or along with the velocity and lightning and thunder, etc. Okay, another equation that we've got is the F of light, which is frequency. So frequency is naturally measured in hertz. So the equation for frequency is F equals V over lambda. That strange looking upside down Y kind of thing there is lambda. So frequency is F measured in hertz. V is the velocity of light. And again, that doesn't change like the velocity of sound does. Okay. And then the upside down Y, the lambda, is wavelength in meters. And then we've got two conversions down here that will become very important in our work. Okay. Because our wavelength needs to be in meters. Depending upon what we're working with, we may be given a wavelength in nanometers, which is our NM, okay? And we would then have to convert it. And then kilohertz is our KH, and 1 kilohertz is 1,000 hertz, just like 1 kilometer is 1,000 meters. Okay, so I'm going to come back to this slide when we need it, and we're going to begin our work with velocity of light on page 366, example 11.3. It says a physicist is watching a thunderstorm. She sees a flash of lightning and then hears a thunderclap 1 second later. If the air temperature is a cool 15 degrees, how far away from the physicist was the lightning formed? Okay. Now, the thing to understand here is that when you see a flash of lightning and then hear a thunderclap 1 second later, basically the two originate at exactly the same time, because the flash of lightning travels so quickly. So they are pretty much one and the same as far as the speed. Okay, so we have 1 second is time, 1.00, 3 significant digits, and the temperature is 15 degrees, and that is going to be important as far as the application of this problem. And we're looking for how far away from the physicist was the lightning formed. The distance or the displacement is our unknown, okay? So what we need to understand here is that in a consistent, constant temperature, sound waves move with a constant velocity, okay? So if we utilized this equation, right, knowing that sound waves move with a constant velocity, the acceleration portion of that displacement equation is gone, okay? Which leaves us with a glorified version of D equals RT, okay? So that is exactly what we're going to need to solve this problem. This is a one-dimensional motion problem, okay? And that is a one-dimensional motion equation. Knowing that sound waves move with a constant velocity in an unchanging temperature, which you may not have known that, but I'm telling you, the acceleration is 0, and we're left with distance equals rate times time, okay? We've got the time. Our distance is our unknown. That means that we need to be able to solve for velocity, okay? So what we're looking for is how far away was the lightning formed, which is one and the same as how far away the thunder was, okay? So because again, light moves so quickly, when you hear the thunder, the light is already traveling, okay? So the distance is our displacement, that's our unknown, and we're looking for the velocity at which the thunder traveled, which is our 331.5 plus 0.606 times our temperature. So if we can figure out the velocity with which the thunder traveled, that's how far away the lightning was formed. We can use that to figure out how far away the lightning was formed. Okay, so the velocity of light, remember our rules. We're going to multiply and follow the rules for the multiplication. 0.606 times 15, no decimals, gives us 9.09, but we need 2 significant digits, so we will use 9.1. Now we will line those 2 values up and add them, and that is what is going to give us our velocity. Okay, so now we know the velocity is 340.6. So our distance or displacement is 340.6 times 1.00, okay? Which is 340.6 still, but we need 3 significant digits. So we don't even need the calculator for that to say that the distance was 341 meters. The lightning, therefore, was formed 341 meters away from the physicist. Okay? Now what we're going to do is move on to the on your owns, okay, which are pretty much the same idea. The on your own 11.5. Okay? If you hear thunder 2.5 seconds after you see a lightning flash, so T is 2.5 seconds, how far away was the lightning formed? So again, we are looking for displacement. How far away the lightning is formed is the same as how far away the thunder was formed because they are simultaneous. So our temperature is given as 20.0. So again, because sound travels at a constant velocity in a consistent temperature, we are going to be using our distance equals rate times time again, because the acceleration portion of that equation goes to 0. So in order to find the rate, that means we're finding the velocity of that particular sound, okay? And then we have 20.0 degrees. So we will figure out 0.606 times 20 to 3 significant digits is 12.1. Okay, so we need to abide by our rules here, and everything lines up exactly the way it should, which is really nice. So we have 343.6. So So the distance that the lightning was formed away from the physicist is 343.6 times 2.5. And of course, we know that there are certain things in the atmosphere that change how long it takes for a sound to travel through air, right? So 343.6 times 2.5 to two significant digits is 860 meters. Okay? Easy enough. One more. Suppose you are watching the start of a race. The official raises the starter's pistol into the air and fires. You see the cloud of smoke rising from the pistol, indicating that it has fired, but you do not hear the sound right away. If you are 402 meters away from the starter and the temperature is 25 degrees, how long will it take you to hear the sound of the pistol firing? Okay, so again, we're looking at distance equals rate times time. We have our distance, our displacement, and we're looking for t, so we need the velocity of that sound. Okay, so all of these formulas now should become very familiar. Okay, and then to two significant digits, 0.606 times 25 is 15. So we'll line up 15. And the significance this time is right here. Okay. So the 5 bumps the 6 up to a 7. So the velocity in 25 degrees Celsius is 347 times t. Okay, and then doing that division, 3 significant digits in each one of those numbers gives us that the time it takes is 1.16 seconds. Okay, which is again almost simultaneously to the gun being fired. Okay, now what we're going to be doing is moving into light as a wave and as a particle. Okay, so on pages 370 and 371, we've got electromagnetic spectrum and the visible spectrum. And if you notice, especially on the visible spectrum, we have our wavelengths that go along with each color given in nanometers. Okay, so that again is why we need the conversion. So when we find a wavelength, we can convert it from nanometers to meters. Okay, so we're going to look at the On Your Own 11.7, okay? And we will be needing to refer back to those tables, okay? So for the On Your Own 11.7, a recently developed laser used in the treatment of skin disorders produces a light with a wavelength of 5.78 nanometers. According to figure 1110, what color is that light? So you're going to flip back, and 578 is between 550 and 600, which is definitely yellow, very, very yellow. So the color of the light that has a wavelength of 578 nanometers is yellow. Okay, now we're looking for its frequency. Okay, so that frequency equation is F equals the velocity of light over the wavelength in meters. All right, so what we need to do is we need to convert the wavelength of 578 nanometers to meters. So here's our conversion. 1 nanometer is 1 times 10 to the negative 9th meters. Okay, so when we do that on our calculators, and this will become very easy to catch on to the rules, so we won't need to do this conversion every time. So 578 times 1 times 10 to the negative 9th gives us 5.78 times 10 to the negative 7th. And what we'll notice then is in every conversion, the decimal will shift 2 places to the left, and the power will go up by 2. Okay, so now we've got our wavelength in meters. So we're looking for the frequency. Okay, light travels at a speed of 3.0 times 10 to the 8th meters per second, and our frequency, or our wavelength, is 5.78 times 10 to the negative 7th. So when we do the division, we've got 2 significant digits in the numerator and 3 here in the denominator. So we need to keep 2 of them. So you'll plug that into your calculator and you will get 5.2 times 10 to the 14th hertz. Okay, simple enough. In 11.8 on your own. As shown in figure 11.9, the waves used to send radio signals are electromagnetic waves. I often listen to a radio station that transmits waves with a frequency of 1240 kilohertz. What is the wavelength of these waves? Okay, so frequency equals the velocity of light over wavelength, but our frequency is in kilohertz and it needs to be in hertz. So we will change that using our conversion. 1240 kilohertz times 1 kilohertz down here. So our labels cancel, and that's the same as 1000 hertz. Okay, so when we do that, we will get, so what we've got is 1240, and we're going to throw 3 extra zeros on the end of that. Okay, so I'm going to write that here. We've got our 1240, and we're throwing the 3 extra zeros on the back. Okay, and the velocity of light never changes. And we're looking for the wavelength. And that wavelength now will naturally be in meters. So mathematically, the wavelength multiplied over on the right cancels out. Therefore, you multiply it over on the left. Then you divide away your 1,240,000, okay, which is still a whole lot less than the speed of light, okay? And then we will get the wavelength, and that will be, again, in meters, okay? So your wavelength will be you've got 2 significant digits here, and you've got 3 in the bottom, Remember, all those zeros behind don't count. Okay? So 240 meters is the length of that particular wave. Okay, you doing all right, guys? Should be relatively simple. Now, what we're going to do is backtrack a little bit to light as a particle, and that's where all of this information is going to be very important, okay? Because we start to work with work functions, photoelectrons, and etc. Okay, so we're going to look at a simplified explanation of what work function is. Okay, so light hits metal, and some of the electrons natural to the metal will absorb some of that energy. If the energy is great enough, the attraction between the electrons and the metal can be overcome. Work function tells us how stubbornly a metal holds its electrons, and in turn, how much energy light needs to supply to break that bond. The energy needed to overcome that stubbornness is in this equation here. E equals HF. Okay? E is the energy required by the light to break the bond. F is frequency, and H is Planck's constant. And we have two different values for that. It depends on what we are given in our problem. It's 6.63 times 10 to the negative 34th. If we're dealing in joules times seconds, okay? Or if we're given our information in electron volts, which is that EV right there, then we would use 4.14 times 10 to the negative 15th. You don't need to worry about converting, although the conversion has been supplied there for you. So you don't need it though, because depending upon what the problem gives you, we have both versions, so to speak, of Planck's constant. So we are going to use that idea in example 11.4. Okay, so example 11.4, and here's the information, okay? Sodium metal has a work function of 2.28 electron volts. So that should tell you right away what value of Planck's constant that we are going to need to use. Okay, so let's write that down. Well, if blue light, this is what I meant to say, let's write this down now, our information. We have lambda, the wavelength, is 4.25 times 10 to the negative 7 meters, so we don't need to worry about changing that. If blue light is shined on sodium, what is the maximum kinetic energy of the electrons that are emitted from the metal? In other words, if this blue light shines on this sodium metal and enough light is shined that some of the electrons break free, we can use that same equation along with the frequency equation to find the maximum kinetic energy of the electrons. Okay, so we're looking at using E equals HF, and we're looking for maximum kinetic energy. So in order to find frequency, okay, we're looking for E. E is our unknown, but we need frequency. H is already known in electron volts. So frequency is the speed of light over the wavelength, which is why we were given the wavelength, okay? So 3.0 times 10 to the 8th divided by our wavelength in meters, and that will give us our frequency. And our frequency to two significant digits is 7.1 times 10 to the 14th, and that is in hertz, which is the same thing as 1 over 1 second. Okay, so the energy that we are looking for then can be found by using the version of Planck's constant that is already in electron volts. So 4.14 times 10 to the negative 15th times our frequency. All right, so we find that that energy is 2.9 electron volts. Okay, so when you multiply Planck's constant times your frequency, you get 2.9 electron volts. So the amount of kinetic energy that the electrons have is going to be 2.9 minus the work function of that metal, which was 2.28. So that's the amount of energy that the electrons will have when they break free, given enough energy from the light. So let's line this up over here. So 2.9 minus 2.28. Okay, and we are going to round right here. Okay, so 2.9 minus 2.28 is 0.62. So all we need is what's in our circle there, and we get 0.6 joules, because remember, all energy, or 0.6 electron volts, which kinetic energy, electron volts. Okay, because we were given electron volts. Okay, so we're going to do our on your owns. Okay, 11.9, and actually we're going to forego 11.10, and we're just going to do the on your own 11.9. Okay, cesium has a work function, so let's just put that up here too. Cesium has a work function of 2.14 electron volts. Okay, that means it hangs on to its electrons with that amount of stubbornness per se. Okay, if green light, which has a wavelength of 501 nanometers, is shined on cesium, what is the maximum kinetic energy that the electrons will have as they leave the metal? Okay, so we are going to be using Einstein's equation. Okay, that's our energy required. So we need to find that and then use the work function value of cesium. Okay, so in order to use frequency in our equation, we need to solve for it. So the velocity of light over, except we have nanometers, and we are going to need to convert from nanometers to meters. So recall our 501, actually, let's do the conversion first, and then we'll write all of our information. So 501 nanometers, and remember, we have 1 nanometer is the same thing as 1 times 10 to the negative 9th meters. So remember, we said the rule would be that you're going to move the decimal 2 places to the left, which raises the power by 2. Okay, now we have our wavelength. So the energy that we're solving for is Planck's constant in terms of electron volts. And then we have 5.01 times 10 to the negative second as our, wait a minute, E equals HF. I needed that to solve for frequency. Okay, so let's solve for frequency first. V, there we go. There's where we're going to use our wavelength. All right, redo, here we go. Okay, now we're going to plug in our wavelength and come up with our frequency. Okay, so doing that, we have 2 significant digits in the top, 3 in the bottom. So we round to 2 and get that the wavelength is the frequency is 6.0 times 10 to the 14th hertz. Now we can use Einstein's energy equation with the electron volt version of Planck's constant times that frequency that we just solved for. Okay? Which gives us an energy, 2 significant digits, of 2.5 electron volts. Okay? So the kinetic energy that the electrons will have as they leave that metal is 2.5 minus the given work function. So we'll line those up just like last time. Okay, 2.5 minus 2.14. And here is where we round. Okay, and we get 0.36. So obviously the 6 bumps up the 3, leaving us with 0.4 electron volts. Okay? All right. So now what you will be able to do is the rest of the practice problems. Okay? Complete the remaining practice problems at the end of this chapter, because the ones that we did before pertained to the math of sound, and these now, the remaining, it's only 3 or 4 of them I think, are the math of light. Okay, so complete the remaining practice problems for this chapter. And when we have a call next week, we can answer any questions pertaining to any of this, and then you'll have your test. Okay. See you guys.